Hello and welcome to the microwave engineering lecture titled Impedance Transformation on Smith Charts. In this lecture, we'll learn how to do impedance transformation calculations on the Smith chart, and I'll give one example. Recall in previous lectures that the impedance transformation formula was given by this expression. This formula can now be written in terms of the reflection coefficient gamma. Using some trigonometric identities and some algebra manipulation, we arrive to the normalized input impedance in terms of the reflection coefficient. Now, what does this formula mean? Recall that the reflection coefficient is given by the magnitude of the reflection coefficient times e to the j theta, in which theta was the angle in which we move along the Smith chart counterclockwise. If we substitute this expression into this formula, the equation can be written as this. This means that when we move along the transmission line, we are simply changing the phase of the reflection coefficient. As we move away from the load and towards the source, we must subtract phase from theta. On the Smith chart, we rotate clockwise. If we move away from the source and towards the load, we add phase from theta, and on the Smith chart, we rotate counterclockwise. Notice that in the Smith chart, a complete rotation corresponds to moving along the transmission line a distance of half a wavelength. Now, these are the steps to do impedance transformation calculations on the Smith chart. The first step is to plot the normalized load impedance on the Smith chart. The second step is to move clockwise around the middle of the Smith chart as we move away from the load and towards the generator or source. Remember that one full rotation is moving half a wavelength in the transmission line. The final point is the input impedance on the line in terms of wavelengths. You can help yourself by looking at the outer circles to see how many wavelengths you are traversing along the Smith chart. This is an example on how to do impedance transformation on Smith charts. We have a transmission line that is connected to a load. The question is, what is the impedance of this transmission line with intrinsic impedance of 50 ohms and load impedance of 50 plus j25 ohms at a distance 0.67 wavelengths away from the load? Using the impedance transformation formula, we can substitute the values to arrive at the normalized input impedance. We can also do the calculation on the Smith chart. The first step is to plot the load impedance. In this case, the normalized impedance is 1 plus j 0.5. So this is the point where it is located. Now, to do the impedance transformation, we walk away from the load a distance of 0.67 wavelengths. Since the Smith chart repeats every half wavelengths, traversing 0.67 wavelengths is the same as traversing 0.17 wavelengths. In this case, we draw a line from the origin crossing through the impedance point and out of the circles. Here in the outer circle, we can see that we start at 0.145 wavelengths on the Smith chart. We move along clockwise away from the load a distance of 0.17 wavelengths, and we arrive at 0.315 wavelengths. Now we look at the intersection of the line and the visware circle at this distance. The reflection at the load will be the same regardless of the length of the line. Therefore, the visware will also be the same. In this case, the input impedance is, as expected from the formula, equal to 1.3 minus j 0.5. Denormalizing the input impedance gives us a value of 65 minus j 25 ohms. And this is how you do impedance transformation calculations on the Smith chart.